In the last class, we have analyzed single phase auto transformer, and we have shown that when the requirement of electrical isolation is not very important and the voltage conversion ratio is close to unity, then use of auto transformer offers significant advantage in terms of copper saving, loss saving, etc. It is possible to have auto transformer connection for 3-phase transformers as well. For example, let us see a 3-phase auto transformer connection with high voltage side star connected. This is the neutral, where these are the line terminals A2, B2, C2. This is the neutral connection, capital N. This is the HV side. We can very well have tappings on each individual winding and have terminals A2, B2, C2 and the same terminal as N. So, if we draw the, so this is capital A1 and small a1, this is capital B1 and small b1, this is capital C1 and small c1. So, if we draw the line to neutral phasor diagram, this is the A phase, this is B phase, this is C phase. So, this is the point N, this is A, that is A2, this is B, that is B2 and this is C, that is C2. Since we are putting tappings here, the voltages, these are the points A2, B2, C2, the voltages A2, A1 will be in phase with A2, A1. So, this is also the point small n and this is the point A2, this is point B2 and this is point C2. Hence, we see it is possible to have a 3-phase star connected auto transformer. Now, if we connect the windings in delta, that is, we again have three HV windings connected in delta, that is, this is A2, A1, B2, B1, C2, C1. A1 is connected to B2, these are terminals A, B and C. A1 is connected to B2, B1 is connected to C2 and C1 is connected to A2. the line voltage phasors will be A2, A1, B2, B1, C2, C1. This terminal we are calling A, this terminal we are calling B, this terminal we are calling C. That is the junction of A2 and C1 is A, B2 and A1 is B, and C2 and B1 is C. Now, suppose we do the same thing, that is we put certain tappings here. Normally, when I have a 3-phase autotransformer, they are taken from the same percentage tapping of each winding. That is, the voltage this part, this part, this part are all same in magnitude. Now, let us call these A2, B2, C2. So, voltage A1 small a2 will be here, B1 small b2 will be of equal magnitude, and C1 small c2 will be of equal magnitude. So, the voltages, this is the point A2, this is the point B2, and this is the point C2. This is the phasor diagram. We can call these points also small a1, small b1, small c1. That is, this point is also a1, this point is also b1, and this point is also c1. So, the line voltage A2 B2, B2 C2 and C2 A2, A2 B2, C2 A2 and B2 C2 forms a phasor like this. Now, when we compare the line to neutral voltage phasors, we see that in a star-star connected 3-phase autotransformer, the line to neutral phasor, the angle between the line to neutral phasor is 0 irrespective of the position of this tapping. So, this is always a star-star 0 degree connection. However, when a similar arrangement made with a delta-delta connected autotransformer, we see that the line to neutral phasor of the HV and LV side, the angle between the line to neutral voltage phasor of the HV and LV side actually depends on the position of the tapping. Therefore, if we change this tapping, this inner triangle will rotate. Hence, the line to neutral voltage phasor of the LV side and the line to neutral voltage phasor of the HV side, the angle between them will depend on the voltage ratio. So, this is one characteristics of delta-delta connected 3-phase autotransformer. Otherwise, the rest of the discussion regarding auto transformer is similar to that of a single phase transformer and can be in fact analyzed on per phase basis in a similar way to a single phase transformer, single phase auto transformer. It should be noted, however, that for auto 3 phase auto transformer, the HV and LV side connection are always same, that is, it can be only either star star connected or delta delta connected. However, star delta or delta zigzag, delta star, these connections are not possible with 3 phase auto transformers. However, 3 phase 2 winding transformers, many of these connections are possible, and one such connections we have seen to be the star star connection, that is the high voltage side star connected, the low voltage side is also star connected. In many cases where the low voltage side is supposed to supply unbalanced loads and in fact single phase load, it is preferable to provide a neutral connection. However, we have observed one problem with this star star neutral connected 3 phase transformer is that the co-phasor currents, that is the zero sequence current of the low voltage side load current and the third harmonic or triplen harmonic currents cannot flow, reflection of that current cannot flow on the high voltage side, which has a isolated neutral. Hence, this produces third harmonic flux distortion. In order to avoid that, some path must be provided for the third harmonic current on reflected third harmonic current, so that the third harmonic flux can be cancelled. This can be done by a delta connected winding, a third delta connected winding. When we provide a delta connected winding like this, then the co-phasor current, the zero sequence and the triplen harmonic currents can circulate within the delta winding, thereby cancelling the co-phasor MMF completely. In many cases, such a winding is provided and those transformers are called the 3 winding transformer. So, the third winding is called the tertiary winding. Sometimes also called the stabilizing winding, particularly when the purpose of this is to provide a path for the co-phasor current. This is called a stabilizing winding. However, it is not essential that this third winding be used only for stabilization purpose. It can be used for other purposes. For example, it can use, if this is used in a substation, this third winding can be used to supply auxiliary power, which are at a very different voltage than the conversion ratio of this transformer, or this can be used to connect a capacitor bank for supplying leading var to the bus. Now, in this lecture we will see how to analyze this 3 winding transformer. For that, let us assume that we have a 3 phase transformer with star connection of 2 windings. This is the primary or high voltage winding, this is the low voltage secondary winding, and let us say this is the tertiary winding. Which is delta connected. Now, when we supply sine wave voltage to this winding and load them with a balanced load, we have seen that a 3 phase transformer can be analyzed on per phase basis. Hence, by the similar argument, the 3 winding transformer can also be analyzed per phase basis, and on steady state, if we consider a single phase of all the 3 windings, we can write the applied voltages and the currents as follows by referring all the voltages to the high voltage side. Let us say the applied voltage here is V A, then V A can be written as R A into I A these are, let us say, capital A, small a, and A tertiary, B tertiary, C tertiary. V A equal to R A I A plus J omega L A I A plus J omega mutual inductance between primary and secondary, that is L A A or M A A into the secondary current reflected to the high voltage side, that is I A dash plus j omega mutual inductance between the high voltage and the tertiary winding, that is A T I A T dash Similarly, for the secondary winding referred to the high voltage side can be written as V A dash equal to R A dash I A dash plus J omega L A dash I A dash plus J omega. Now, this being symmetrical, this will still be M A I A plus J omega M dashed A T I A T dash. And for the tertiary winding, we can write V A T dash equal to R A T dash I A T dash plus L A T dash I A T dash J omega plus J omega M A T I A plus J omega M A T dash I A dash. Similarly, for other phases we can write these equations. Hence, we can also write by defining L M to be the magnetizing inductance due to the flux that links all the phases. We can write V A equal to R A I A plus J omega L A minus L M I A plus J omega M A minus L M into I A dash plus J omega M A T minus L M I A T dash, where the dash refers to the currents referred to the HV side, plus J omega L M into I A plus I A dash plus I A T dash. Similarly, V A dash can be written as J omega M A minus Lm into Ia plus R A dash I A dash plus j omega L A dash minus L m into I A dash plus j omega m A T dash minus L m I A T dash plus j omega L m I A plus I A dash plus I A T dash. And V A T dash equal to j omega m A T minus L m I A plus j omega m E A T dash minus L m into I A dash plus R A T dash I A T dash plus j omega L A T dash minus L m I A T dash plus j omega L m into I A plus I A dash plus I A T dash. Now, if we assume that the magnetization current of this transformer is negligibly small, then we have I A plus I A dash plus I A T dash equal to 0. Let us also define x11 to be equal to omega into L A minus L m, x22 dash equal to omega into L A dash minus L m, x33 dash equal to omega into L A T dash minus L m. Similarly, let us define x12 to be equal to omega into L m A A minus L m, x13 equal to omega into m A A T minus L m, and x23 equal to omega into m a a t dash minus L m. Then we can write V A equal to R A I A plus J x 11 I A plus J x 12 I A dash plus J x 13 I A t dash. V A equal to J x 12 I A plus R A dash I A dash plus J x 22 I A dash plus J x 23 I A t dash, and V A t dash equal to V A t dash can be written as J x 13 I A plus J x 23 I A dash plus R A t dash I A t dash plus J x 33 I A t dash, from which we can further simplify it to V A minus V A dash equal to R A I A plus J x 1 I A minus J x 2 dash I A dash minus R A dash I A dash. Where we have defined x 1 to be equal to x 11 minus x 12 minus x 13 plus x 23, and x 2 dash has been defined as x 23 minus x12 plus x13 x22 minus x23. Similarly, we can find out V A minus V A_T dash. This is given by R A I A plus J x1 I A minus J x3 dash I A_T dash minus R A_T dash I A_T dash, where x3 dash has been defined as x33 dash plus x12 minus x13 minus x23. These equations then suggest the following equivalent circuit for the 3 winding transformer. This voltage is V A, this voltage is V A_T dash, and this voltage is V A dash. Hence, this impedance is R A_T dash, this is minus, this is J x3 dash, this is R A dash, this is J x2 dash. Current flowing into this circuit is I A, current flowing into this circuit is I A_T dash, and the current flowing into this circuit is I A dash. This circuit is completed by putting a magnetization branch just like a 2 winding transformer like this, also referred to the high voltage side. This is R m, this is J x m, and this is I 0. where I0 equal to IA plus IA dashed plus IAT dash. So, this is the equivalent circuit of a 3 winding transformer. The shunt branch parameter as usual can be determined from the open circuit test, that is applying rated voltage to any one of the 3 windings and keeping the other windings open. Similarly, the series branch parameter, that are these parameters, can be obtained from short circuit test. However, here 3 sets of short circuit test are to be conducted. One set will be voltage to HV side, LV and tertiary, these will be shorted. Next, you apply voltage to LV side, HV and sorry. In this case, you have to do 3 sets of short circuit test. One, voltage to HV side, LV side shorted, tertiary winding open. Then voltage to HV side, LV side open and shorted is tertiary winding. Then voltage to LV winding, HV winding shorted, HV winding is left open and short circuited tertiary winding. From these 3 sets of short circuit test data, we can find out the parameters of a 3 winding transformer. Let us see how through an example. Let us say we have a 66 kV by 33 kV by 11 kV Y deconnected 3 winding transformer. Then the winding voltage and KVA ratings are as follows. The HV winding or the primary winding, that is 66 kV and KVA rating is 3.5 MVA. Secondary, this is Y connected, this is also Y connected, this is 33 kV and its KVA rating is 2.5 MVA. The tertiary, this is delta connected, this is 11 kV and its MVA rating is 1.0 MVA. In order to find out the series branch parameter of these 3 winding transformer, the following tests are conducted. So, serial number, then winding excited, then and the winding shorted, the line to line voltage of excitation, voltage, input current, standard data for a short circuit test, input power. So, serial number 1, winding excited is the 66 kV winding, the shorted winding is the 33 kV, the applied line to line voltage on the 66 kV is 2.5 kV, that circulates a current of 22 ampere through the HV winding, and the input power is 7.5 kilowatt. The second test, again the excited winding is the 66 kV winding, however, this time the shorted winding is the 11 kV winding, needed to apply 1.5 kilovolt to circulate a current of 8.75 ampere and the input power was 2.25 kilowatt. In the third test, the excited winding now is the 33 kV and the shorted winding is 11 kV. Applied voltage is 1 kV. The current circulating in the 33 kV winding is 17.5 ampere and the input power is 3.0 kilowatt. Now, referring to this test data, we can see if we keep a winding open, then that resistance does not come into consuming power from the input power, and if we neglect the magnetization branch during short circuit test, then the total power that is consumed in the two resistances of the 3 winding transformer, and with one of the windings open, these two currents are almost same in magnitude, because this winding is open and the no load current we are assuming to be negligible. Hence, for the first test data, the input power of 7.5 kilowatt is consumed in the high voltage winding and in the 33 kV winding, that is in this winding and in this winding, that is in this resistance and in this resistance. So, the equivalent resistance of the 66 kV and the 33 kV windings referred to the 33 kV side will be, let us call it RYY. This should be equal to 7.5 into 10 to the power 3 divided by 3 into the circulated current is 22 amperes. This gives me a value of 5.165 ohm. By the similar argument, the impedance will ZYY will be equal to 2.5 kV this gives me 65.61 ohm, hence XYY equal to 65.41 ohm. Similar arguments RYD equal to 2.25 into 10 to the power 3 divided by 3 into 8.75 square, that comes to 9.8 ohm, and XYD comes to be 98.49 ohm. ZYD is 99 ohm. R dashed YD, it is referred, R dash means referred to the 66 kV winding, R dash means referred to the 33 kV winding. This comes to 3.265 ohm, and XYD dash comes to be 32.83 ohm. Now, these are to be referred to the 66 kV winding, that is RYD equal to 66 by 33 whole square RYD dash, this gives me 13.06 ohm. Similarly, XYD is 66 by 33 whole square XYD dash, this comes to 131.32 ohm. Now, the generic equivalent circuit of a 3 winding transformer, as we have seen earlier, is something like this. This is R capital Y, this is X capital Y, this is R small y, this is X small y, this is R small d, this is X small d. This voltage is 66 by root 3 kV. This voltage is 33 by root 3 kV. This is 11 kV. Now, RYY equal to RY plus R small y. Similarly, RYD equal to R capital Y plus R small d, and R small d equal to R small y plus R small d. Therefore, R capital Y plus R small y plus R small d equal to half of R y y plus R y d plus R small y small d. This comes to 28.02 ohms. Hence, from here we can find out R y equal to 0.95 ohm, because we know R capital Y y. R small y comes to 4.21 ohm and R small d comes to 8.85 ohm. In a similar manner, X y comes to 16.39 ohm, X small y comes to 49.22 ohm and X small d to 82.3 ohm. Hence, we see that from a set of 3 short circuit test data, we can find out the equivalent circuit parameters of a 3 winding transformer, which can later be used in the usual manner to solve or analyze different operating situations in a 3 winding transformer. Thank you.